In this video, we're going to start talking about the power rule. So by the end of this lesson, you should be able to answer the following little question: what functions' derivatives can be calculated using the power rule, and how do we find these derivatives? And as a reminder, by the end of Unit 2, which is lessons 7 through 12, you should be able to answer the following big questions: how do we make finding derivatives easier, and what is the point of finding derivatives? So let's start by giving some examples of equations of horizontal lines. So that would be something like y is equal to 2, or y is equal to -3. So basically anything where y is equal to a number. Okay? The slope of any horizontal line is 0. So using what we know so far, let's make a conjecture about what the derivative of any constant function, f of x is equal to c, is. Okay, so here's what we want to think about. So we know that a constant function is f of x is equal to c, where c is a real number, but that's exactly what we just wrote above for a horizontal line. Okay, we know that the slope of a horizontal line is 0, and we also know that the derivative is equal to the slope of the tangent line. But in our case, the tangent line is the line itself because it's a line. So we can say that f prime of x is equal to 0 for any f of x equal to c. Okay, so moral of the story, if you have a constant function, so if you just have a number as your function, then the derivative is always going to be 0 for such functions. Okay, so how do we find the derivative of something like x raised to a power now? So we talked about constant functions, that's kind of like the very basic case. Now let's talk about x raised to some powers. So right here you have a little table of functions and their derivatives. So I want you to kind of think about what patterns do you see between the functions and their derivatives. So you should pause the video here for a couple of seconds and think about that, and then we'll talk about it together. So what I'm noticing two things. I'm seeing that the exponent in each function becomes the coefficient in each derivative. So exponent from each function becomes the coefficient in the derivative. And another thing I'm noticing is the difference in the exponent between the function and the derivative is 1. So it seems like for each function, the derivative's exponent decreases by 1. So derivative's exponent is 1 less than the function's exponent. So let's see if we can sum this up in a mathematical formula. So what we're saying here is we're saying the derivative of some x raised to some power n is definitely going to be something where the power is 1 less, so we take 1 away from the exponent, but we also said that the old exponent becomes the coefficient. So the formula might look something like this: n times x to the n minus 1. Okay, so if we go down to the next page, it turns out that that is called the power rule. So taking the derivative of x to the n, where n is any real number, requires the power rule. And this rule is exactly what we wrote down in the previous box. So we have d dx of x to the n is equal to n times x to the n minus 1. So we can sum that up by saying the exponent comes down and we subtract 1 from the exponent. So let's practice a couple of examples. So first we're going to find the derivative of 3x cubed plus 2x squared minus x plus 3. So as always, we start with our problem statement. In the second step, I'm going to apply the power rule. So notice that in each term, so this kind of draws back on our lesson 7, where we're taking the derivative term by term, but now we notice that each of those terms requires a power rule or a constant function rule because they're all powers of x. So when we apply the power rule, notice from here to here, the 3 comes down to the front, and we subtract 1 from the exponent. Here, the 2 comes down to the front, and we subtract 1 from the exponent. And finally, on the negative x, the 1, so it's an understood exponent of 1 right here, the 1 comes down to the front, and we subtract 1 from the exponent. So all we do from the second to the third step is just simplify everything that we did for the power rule. And so we should end up with 9x squared plus 4x minus 1. So notice that constant of 3 has disappeared because we used that rule of, oh, my pen's getting slow again. Come on. Okay. We'll see what happens. All right, so, oh, there we go. Okay, so f prime of x, or f prime of 3 is equal to 0. Or maybe, well, maybe I'll just do it like this. So the 3 turns into a 0, and that's why it's missing from the derivative. Okay, so not too bad. Power rule is pretty friendly. Let's look at another example that gets slightly more difficult. So this time we want to find the derivative of f of x is equal to 4x to the negative 1 minus 5 over x squared. Okay, so the trick to this one is recognizing that we can rewrite certain powers of x so that we can use the power rule. So this function is given to us in a form where the power rule is not feasible as it's given, but if we change it to a slightly different form, then we can use the power rule. So as always, we start with our problem statement, so we rewrite our problem, and then we know that to use the power rule, we need to just have x raised to some power. That power can't be in a denominator, so we need to find a way to get this x squared out of the denominator. And the way that we do that is we use negative exponents. So when we move x squared to the top, the exponent becomes negative 2. So we can summarize this by move x squared to numerator with negative exponents. Okay, from there we can use the power rule. So now all of our powers of x are in the numerator, so we can go ahead, bring our powers down, subtract 1 from each power. So that's what's happening here. So we bring down the negative 1 and we subtract 1 from the power. And then here we bring down the negative 2 and subtract 1 from the power again. So be a little careful with negative numbers because the subtraction can get a little confusing. So in this step, we're applying the power rule. And then in the next step, we're just simplifying. So we're just taking care of that multiplication and that subtraction in the exponents, and you should end up with negative 4x to the negative 2 plus 10x to the negative 3. Now I'm going to do one more step just because if you see answers pop up on your WebAssign homework, they'll typically change things back to where an answer doesn't have negative exponents. So I'm just going to do that really quickly in the next step and show you how that works. So basically all we're going to do is to turn these exponents back positive is we're just going to move them back down into the denominator. So this negative 4x to the negative 2 becomes negative 4 over x squared, and 10x to the negative 3 becomes 10 over x cubed. So we can say that that is make all exponents positive. And again, this last step is not entirely necessary, but when your answers pop up on WebAssign, they'll typically be in this form. So just so you're not confused that, the answer you got may look a little different from their answer key. Okay, one last example for straight up derivatives with power rule. So this time we have 3 times the square root of x minus 5 times the cube root of x. So kind of like the negative exponents, the point of this problem is to show you that there could kind of be another way that the power rule could be disguised. So we start with our problem statement, as always. And here what we're going to do is we're going to think about how we can turn radicals into exponents. And the way we do that is through rational or fractional exponents. So if you need review with this, make sure to ask people so that you're not confused. But so we can turn radicals into exponents by thinking about them as fractions. Okay, so like a square root would turn into a 1/2 power, a cube root would turn into a 1/3 power, and you could have some different, like it doesn't always have to be 1 in the numerator, it could be some different things, but the idea is we want to turn this into an exponent. So we can summarize this first step as turn radicals into fraction exponents. Okay, now that we have our radicals in terms of fraction exponents, we can still apply the power rule. Okay, it's just be a little careful when you're doing subtraction with fractions. I know everyone's not a big fan of that, so just make sure you're a little careful with your arithmetic, but other than that, it's the same power rule. So for 3x to the 1/2, we bring down the 1/2 and we subtract 1 from the exponent. For negative 5x to the 1/3, we bring down the 1/3 and we subtract 1 from the exponent. So here, all we're doing is applying the power rule. And from there, we just have to simplify a bit. So we can multiply those coefficients in the front of each term, and we also carry out the subtraction in each exponent. So here you should have 3/2 x to the negative 1/2 minus 5/3 x to the negative 2/3. So like I said, just be a little careful with the subtraction because you could end up with a negative exponent in your answer. And then finally, once again, I'm just going to rewrite that final answer using back to radicals and back to positive exponents. So rewrite with radicals and positive exponents. And once again, this step is not entirely necessary for a test purpose, but your answers on WebAssign could appear like this. It will accept this second to last step, but when it shows you the answer key, it could show it to you in this form. So I want to make sure that you understand that those are equivalent. Okay, so to go from x to the negative 1/2 to a radical positive exponent, we simply write square root of x in the denominator. And for x to the negative 2/3, that'll be the cube root of x squared, but written in the denominator. Okay, so that's our third example. Now let's try a little word problem. So it's estimated that Y years from now, the average SAT mathematics score of the incoming students at an Eastern Liberal Arts college will be S of Y is equal to negative 6Y plus 582. So part A just says derive an expression for the rate at which the average SAT score will be changing with respect to time Y years from now. So a key word in part A is derive an expression for the rate at which the average score will be changing with respect to time. So anytime you see rate, the first thing you should think is derivative, because we know derivative is instantaneous rate of change. And we also know that y is already a time variable, and we know s represents the SAT score. So if we want the rate of change of the score with respect to time, what they're really asking for is just s prime of y. Okay, and we can do that. So this is a linear equation. We can take a derivative with a power rule. So s prime of y is just going to be negative 6 because we move that exponent of 1 on the y down, and then if we subtract 1 from the exponent, we get 0, meaning that it's just going to be a number for our derivative. Okay, So that's our derivative. Part B says, what is the significance of the fact that the expression in part A is a constant? Well, s prime of y, a constant, means that the average score changes by the same amount each year. So that's exactly what constant means. It means steady, not changing. So if our derivative is a constant, it means our average score is going either up or down by the same number of points each year. Part B also says, what is the significance of the fact that the constant in A is negative? So s prime of y negative means that the average score decreases each year. And that makes sense, right? Because if something is changing in a negative way, that typically means that it's getting smaller or it's decreasing. Okay, and now we're just going to go back to lesson 7 when we talked about higher order derivatives, and we're just going to practice doing a higher order derivative with power rule mixed with a couple of your derivatives from lesson 7, so those basic functions. So we're given f of x is equal to x squared minus 3x plus cosine of x minus e to the pi. So let's find the first derivative of this function. So the first term is x squared, which requires a power rule because it's x to the power. So we can bring down the 2 to the front, and then we have x to the 2 minus 1, which will just be 1. So we can just write 2x. Negative 3x, we can also use a power rule. So that's an understood exponent of 1. So if we bring the 1 down, we just have negative 3x to the 1 minus 1. But 1 minus 1 is 0, and anything to the 0 is 1. So really what happens is this x just goes away. Now we look at cosine of x. Thinking back to your basic derivatives, hopefully you're studying those, the derivative of cosine of x is going to be negative sine of x. And finally, negative e to the pi. Don't let those symbols fool you. E is a number, pi is a number, so any number raised to another number is just a constant. So this one is going to go to 0. So our first derivative is 2x minus 3 minus sine x. Okay, let's try the second derivative. So f double prime of x. If we start with our first term of 2x, then we can use a power rule on that. So it's an understood exponent of 1. So we're still going to have the 2 because 2 times 1 is 2. X is going to disappear because the exponent will change to 0. If we look at negative 3 is a constant, so that's just going to be 0. And then finally, negative sine of x, if we think back to our derivative table from lesson 7, the derivative of negative sine of x is going to be negative cosine of x. Okay, so that's f double prime, 2 minus cosine of x. Now let's look at f triple prime of x. Okay, so if we look at the first term of f double prime, we have a 2, which is a constant, so that's gonna disappear, that's just 0. And the derivative of negative cosine of x is going to be negative times negative sine of x, which just gives us positive sine of x. So the third derivative of that function, f of x, is just sine of x. Okay, so that's some practice with some higher order derivatives. So actually that's it for lesson 8. So we did the power rule, that's about it. So just make sure you check your understanding to make sure you can answer that little question for this lesson. Other than that, that's the end of this lecture.